we saw earlier that if we oversample, we have too much data to handle, and when we undersample, we get a signal that's reconstructed that shows clearly that there is a signal that wasn't there. So we can't have that. So there is a minimum sampling rate. So let's take a look. When we are sampling close to the minimum sampling rate, what happens? So if you look at the sinusoid here, again we are using the 1 volt peak 1 hertz frequency, and the sampling rate now is 2.2 samples per second. Now at 2.2 samples per second, we will get at least 2 samples per cycle. So in 2 samples per cycle, we see that in one sample it will be positive, and in another sample the value will be negative. And if you look at the next cycle, it happens also positive, negative, positive, negative. So in other words, every cycle we expect that there will be a transition. So in 1 second there's a transition. So when we pass this sample data to D2A and onto a low pass filter, we find that we are able to reconstruct the correct frequency. However, if you look at the amplitude, the amplitude starts small, becomes bigger, then after a while, after it becomes big, then it will actually drop to a small value. Nevertheless, the frequency is correct, so we can say that the reconstructed signal is correct. So the person who discovered this is called Ngee, and Nike's theorem on the minimum sampling rate is this. Nike's theorem states that to correctly reproduce a signal which contains the highest frequency component, Fm, we must sample the signal at a minimum rate of 2 Fm, or twice the signal highest frequency. So therefore, the lowest allowable sampling frequency, Fs, must be twice of Fm. Okay, and this is known as the Nike's sampling frequency, or we short form that as Fn. So Fs, so the sampling frequency should generally be greater or equals to 2 Fm. And when Fs equals to 2 Fm, then we call Fs to be equals to Fn, the Nike's sampling frequency. So what is Nike's theorem? You want to guess? The minimum sampling rate must be twice the signal's highest frequency component. That's the gist of it. And what is sampling frequency? The sampling frequency is twice of the signal's highest frequency component. See, a signal may have frequency, a lot of frequencies in it, but you have to choose the highest frequency component that you are interested in, and that is the that determines the sampling frequency that you must use, the minimum sampling frequency that you must use. Question. So let's take a look. If the maximum frequency of a biosignal is 100 Hz, so the maximum frequency is 100 Hz, so that's Fm equals to 100 Hz. What is the Nike's sampling frequency for the signal? What do you think is the answer? It should be twice, that's right, twice. Okay, twice, so there will be 200 Hz. What is the minimum sampling rate that you must use? You know that if you go lower than the minimum sampling rate, you will have error. So you know that the minimum sampling rate should be the Nike's frequency, which is 200 Hz. So the answer to A is 200 Hz, the answer to B is 200 Hz. Question for part C. Will the system work if we sample at 500 Hz or 500 samples per second? What do you think is the answer? If you remember the waveform, when you oversample, you can reconstruct it quite clearly. So you know that 500 samples per second will work quite well. Okay. So let's look at the aliasing error. In other words, when you subsample, when you subsample a signal, you will get a frequency that is lower than the actual frequency. Why is this important? Well, this is important because when you have a signal source and the signal source is limited to a certain frequency and noise comes in, and noise is higher frequency than your signal frequency, even though you are sampling your signal at more than twice the maximum frequency of that signal, it is an undersampling of the noise signal which is at a far higher frequency. And this undersampling will translate the noise into your signal frequency band. And this noise that is generated is called an aliasing error. An aliasing error is a signal once introduced cannot be removed. So far we have no way of removing it. So let's look at aliasing error. Signal distortion occurs whenever the signal is undersampled, and the sample is known as aliasing error, which we depict as FA, or alias frequency. And the alias frequency can be calculated by this formula. FA equals to the modulus, in other words, the absolute value of Fm minus Fs. Okay, Fm minus Fs, provided that the aliasing frequency that results from this formula is less than the sampling frequency, Fs. If it is not, that means if Fa is greater than Fs, then what you do is you subtract away Fs from Fa until you get the final Fa which is less than Fs, and that will be your answer. Example, if the sampling frequency Fs is 0.6 Fm, this is definitely an undersampling case. The reconstructed signal will have a frequency component that is 0.4 Fm instead of the original Fm. So you put in a signal that has a frequency Fm, you sample it at 0.6 Fm, and the result you get is 0.4 Fm. That's clear. Now what happens if your sampling rate is even lower? You sample it at 0.4 Fm. Okay. Then you get the final result you get is not 0.6 because Fa equals to Fm minus Fs, you expect it to be 0.6, but the answer is actually 0.2 because 0.6 is greater than the sampling frequency, then sampling frequency being 0.4 Fm. So you subtract away 0.4 out of the 0.6 and you are left with 0.2. So the aliasing frequency will always be less than the sampling frequency. So signal reconstruction. Now you've got this stream of data and you want to reconstruct this stream of data. How do you do it? So the computer reads from its memory and it sends it to a digital to analog converter, and from this digital to analog converter you get back your sampled signals. You have to use the same time frame that you sampled at in order to get the right frequency, and you pass it through a low pass filter, and after passing it through a low pass filter you get this nice sine wave back, or some other waveform that you might have sampled earlier. So this reconstructed signal will be accurate relative to the input signal, provided no aliasing error has occurred. So to prevent aliasing error, one of the ways we can do this is we can band limit the input signal. So if you have an input signal that's coming in, you want to band limit it so that only frequencies up to the maximum frequency component of the signal can go through. Any other frequencies that's above will be attenuated. And you do that by using a low pass filter. So here we see how to prevent high frequency noise from introducing aliasing error into the data. You do this by using a low pass filter to reject the high frequency signal. Okay? So the solution, choose the cutoff frequency of the low pass filter to be the maximum frequency component of the signal. So if the signal maximum frequency component of the signal is Fm, you choose your cutoff frequency of your filter to be Fm. Then you set the sampling rate to be faster than the Nyquist sampling frequency. That means you choose it more than 2 Fm, and typically we'll use it about 5 times that of Fm. So 5 FM will be our typical sampling frequency. So for example, if the ECG waveform has a frequency component of up to 100 Hz, we would use a low pass filter that cuts off at 100 Hz. So any frequency component above 100 Hz will be attenuated very rapidly. And our sampling rate will be more than 200 samples per second, because 200 samples per second is twice. So typically we'll use about 500 samples per second.